sorry, there's no camera. Give me 1 second then. Alright, there we go. Why does it look like shit? Alright. Hello. Which I can't see chat if someone's chatting, so maybe I'll figure that out along the way. Anyways. So I started. So I was doing number 15. Let's see. So I did this. Alright, we'll skip these then. 16. Write the contrapositive of the following sentences. Use words or logic symbols and simplify the answer. Try to avoid using the negation symbol or words of negation. Okay, so if k is prime and k is not equal to 2, then k is odd. So this is obviously true because every odd number greater than 2, or sorry, every prime number greater than 2 has to be odd. So for all x and I guess we can say the integers is fine, where x is prime and x is greater than 2, then x is odd. I would think that's how you write that. I can check the solutions after, but it says use words or logic symbols. So if I do my assignments, I'll get a good mark in the course. I'm writing the contrapositive too, so this has to be switched around a bit. So this should be if x is even and x is less than or equal to 2, then contrapositive, this would be flip it. So x is even. Oh, I see, I fucked it up. So if x is even, then x is a prime, or x is composite. Or x is greater than or equal to 2. So the opposite of being prime is being composite. So that's natural, that's going to happen. If x is even, then x is composite, and x equal to 2. I think that's not right though. Oh, then x is a composite or x is equal to 2. B, if I do my assignments, I'll get a good mark in the course. If I don't do my assignments. I will not get a good mark in the course. Oh, then that's really better. I fucked it up. If I don't get a good mark in the course, then I didn't do my assignments. If x squared plus y squared is equal to 9, then x must be between -3 and 3. If x is not less than 3, so basically if it's as long as it's not in that range, then x squared plus y squared is not equal to 9. D. If a is not equal to 0 and b is not equal to 0, then a squared plus b squared is not equal to 0 either. I hope that's right, because I think this is a valid equation. Could be mistaken. I think it is a valid equation. If Anna is failing both history and psychology, then Anna is not graduating. So if, oh, and again, this would be, or because when you flip it, it switches. If Anna is graduating, then she is passing both history and psychology. If anyone wants to know what a contrapositive is again, just a refresher, if you have a statement X or A implies, B, the contrapositive of this, CP for short, is not B implies not A. So A being the statement if Anna is, A being the statement, oh, then she's passing or. Psychology. Okay, so again, A, B. So in this case, this statement, number E, Anna is graduating, would more reference be like A and B implies C, where A is Anna is passing history, and B is, or I guess A being Anna's failing history, and B being Anna's failing psychology. So if you take the not of this, obviously, I guess kind of similar to the Morgan's laws, you have not A or not B. But you flip it because the contrapositive, right? So when you take the contrapositive, you do not C, implies whatever this statement is. Doesn't matter if it's multiple statements, you just take it to the other side. So then it's not A and B. And this becomes not C, implies not A or not B. Thus, you have if Anna is graduating, which is the negation of Anna is not graduating, then you end up with Anna is either passing psychology or she is passing history, which is again the negation of she's failing psychology and she's failing history. What do you find are tautologies, which are a contradiction? Okay, so tautologies are statements that are only true. Contradictions are statements that are only false. So P and not P is clearly a contradiction. You don't have to think about this one, because you can never have P be true and false at the same time. So Like if it's true, then this is true, but this is false, and if it's false, then this is true, but this is false. So it's always false. P implies P and not P. This is because we have P implies P and not P implies P. So I think this one is actually neither. This one might be neither because we have true, right? This is true, false. Oh, it's false. False. But then if P is false, then that's false. But this is also, I think it would be false anyways, because then this one's not false either. And then again, if it's false, then this is true. And this, yeah, so it's the contradiction. That one should have been immediately obvious to me. This is the tautology. Because again, or, so if you're saying like, I will go to sleep or I will not go to sleep. You're going to do something. Like you're either going to go to sleep or you're not going to go to sleep. So one of these statements is guaranteed to be true. There's nothing you can do that's not between going to sleep or not going to sleep. P implies not P. Again, P implies not P is just, I guess, I guess it's not because it's the other way around. So this would actually be true, false. This is false. And then false, this would be true, so this is neither. P and Q imply Q. Okay, so again, anything this is false, so let's just disregard the value of P because at the end of the day, it kind of doesn't matter. So if we just say false, then this thing here is false. So this whole statement is true, if that's the case. Doesn't matter what the value of Q is, as long as P is false. Or I guess as long as Q is false, then this whole statement is true. And now if Q is true, and say P is true as well, it's true. And if P is false, so yeah, again, this is a tautology. It's true for all values of P and Q. $18. In one cartoon, the dog contradicts that concludes that he is a cat. Find the flaw in his argument. What connectors and quantifiers are used? Can you rate this? Any truth table discussed in this chapter. All cats have 4 legs. I have 4 legs. Therefore, I am a cat. So his flaw in his argument is that cats have 4 legs and he has 4 legs. Therefore, he is a cat. But no statement in this comic is false per se. But there is also like a flaw in the argument, assuming that he's just a cat because he has 4 legs. Because there are other animals with also 4 legs. So like elephants have 4 legs, rats have 4 legs, dogs have 4 legs. So he is a dog, but he's assuming that he has 4 legs makes him a cat, which is not true. So the flaw in his argument is that dogs, there are other animals with 4 legs. Not cats are not the only one with 4 legs. So it's not true to just assume that you're automatically a cat because of that. Which connectors and quantifiers are used? So if we read it as a statement, then we can say let A be all cats have 4 legs. Let that be it. And then let B be like, do you have 4 legs? And let C be, they are a cat. Or I guess we don't need to write A because A is always true. So let's just write B and C as B is they have whatever yourself has 4 legs and C being you are a cat. So this would be B being if you have 4 legs implies that C is true. How do I get this off my screen? which is not true. Shit. What? Okay, I'll open the solutions for this one because this one is a little bit of a tricky one for sure. Okay, 19, that sets. Right here, this is a fallacy. The dog says that all cats have four legs, meaning that even if it's arbitrary object, if a cat has four legs. The dog says that have four legs, but cannot include. Oh, it just didn't even. Yeah, so again, like there are other objects with four legs. They just called it like nonsense, which I guess is a valid way to do it. But write a statement. There is no set A for which A is an A without using words of negation. No or not. I guess for every A, which is a subset of the real numbers, A cannot be in A. I think, let's see if that's true. For every set A, we have the A is not A. Okay, well, similar, I just wrote it using quantifiers. Negate the following statements. You may use water symbols in your ampersand file as much as you can. Okay, negation. For all x in A, there is a b in B such that B is greater than x. Okay, so switch the quantifiers around. So there exists an x in A. Such that for all B in B, such that B is less than or equal to x. This is false, obviously. Actually, this might not be false. Overall, it's false, but depending on the sets, it could be true. For any positive real number x, so there exists an x, because I think that'd be for all. X in a set of reals, which you don't have to state because whatever. There is a natural number n for which 1 over n is less than n. So for all n in set of naturals, there is 1 over n that is greater than or equal to x. Okay. This statement is obviously false. Oh, actually, no, same issue. Same is true, because you could actually just let x equal to -1, and then you would get true statements. B is less than x. There's a positive number x such that for all natural numbers we have 1 over n squared. Yeah, okay. 2021. I have to use the washroom pretty badly. 21. Write the negation of the following statement. Okay, I gotta use the washroom. I will be back. bathroom break. Anywho, let us get back to the whatever we're doing. 21. Write the negation of the statements without using the negation symbol. Also, said after whether it is true or false, explain your answer briefly. So, negation for all x in R. There is an x. There is an x. I search that for all y in R. X squared is less than or equal to y squared. This is false, obviously. There is no smallest integer or integer that period that satisfies this equation. It just doesn't exist. Because you could only have, like, let's say, just set y is equal to x minus 1, I think should work. But then if you have, like, let's see, well, if it's a decimal, say like 0.99, then y would be equal to negative 0.1, which would definitely be less. So I think that works. I think that does work for all. 21, 20, oh, this statement is false. There is no smallest positive real number. Okay. This is a B. Holy shit, there's a fucking lot of these. For all x. Okay, so interesting. So this quantifier here is actually outside the statement, so we gotta be a little mindful of that. I can't remember that. Yeah, it should be. So for all x and a, again, for implication, statement remains the same. So x squared is equal to x plus 1 squared. Interesting statement. Okay. And x3 is not in Z. This statement I don't even know what to make of this statement, to be honest. So for all x, x squared is equal to x plus 1. I think this statement is false. I don't think this statement is true. Because if you had, like, let's say 9 squared, oh, well, yeah, 9 squared is not equal to fucking, 9 squared is not equal to 10 squared. So let's see what this thing has to say. The original statement is false. Really? Since x squared is equal to x plus 1 implies only x negative 1 over 2, where x negative 1 over 2, 3 is not an integer. Interesting. Interesting. The original statement is true. Oh, wait, what? There is, oh. Yeah, the original statement is true. Sorry, I was doing the negation. Would probably got this one still right, I feel like, because false is just like the thing you default to. Anyways. For all n in n minus 1 cubed is not equal to, I'm not going to write that down because I got to write the negation anyways. There exists Oh, shit. For all integers. So, basically, if you have three consecutive integers, the first two cannot equal the third one squared. So, let's just say 9. How many good time 9? So, 8 cubed plus 9 cubed is not equal to 10 cubed. Calculator. Definitely not equal to 10 cubed. Okay, so the real statement is false then, because we found one example. Oh wait, the original statement may be true then, because we found one example that matches it. So, can we actually proceed by the contrapositive? So, contrapositive being for all n and n, there exists an n plus 1 cubed that is equal. No, I can't even proceed by contrapositive, the single statement. I don't think the statement is true. Could be wrong, but let's see. Statement is true. Deal. My goodness, where got so many of these to go? Sorry, I was able to let you. Alright, number D. There is an A and R such that. Okay, so important thing to know about this is this statement that we're gonna write now is this original statement is false, but I'll explain why in a minute. D. So for all okay, so shoot. Okay, so the negation of this is true, but the actual original value of this is very, 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 very false, right? So you don't have to look at the second statement. You can look at the first statement. For all x and r, x is greater than 0. That's not true because you have -1, all the negative numbers. So therefore, that's false. And therefore, if a statement is false in an implication, the implication is automatically true. So this statement is true. For all x and r, careful negation. For all x and r. Again, implication. So x squared is less than -1, and this statement stays the same. This becomes an and then not. So and x plus 1 squared is not equal to x squared plus 1. So yeah, this statement looks true. So choose like 1 over 2. Sure, 1 over 2 I think works. Oh, no, never mind. -1 over 2. Oh, wait. This is if x squared is less than or equal to -1. The only number that satisfies this equation is 0. Is 0. So 0 and 0 plus 1 is 1 is equal to, so this, the original statement is actually true. Let's see. The statement is true since the original statement is true since x squared minus 1 -1 is true vacuously. I wouldn't have said vacuously, but okay. Because I guess problem is there's no x squared. It's false for all numbers, yeah, I guess. Oh, what am I saying? Even if it's true for 0. I'm so stupid. 0 is greater than -1. My bad. Yeah, the original statement is true vacuously. Oh boy, how many more have you got? Ladies and gentlemen, hurry up. F. There exists an X and R such that, so again, this is the entire statement. So, okay. Okay. There exists an X and R such that for X greater than 0 and for all N and N, so this statement is true because you could have N be equal to any number and this statement is true. The original statement is false. Let's see if we're right, everybody. The original statement is true. I am wrong. So let's read this again. For all X in R, X greater than 0 implies that there exists an N such that N taught X is greater than 1. Okay. Definitely true. Definitely true. What if you had, but what if you had X is equal, oh, X has to be great. Yeah, what if you had X equal to 1? That's true, so that would imply it. Then there exists an N. Oh, and then you do like 10. Okay, so why is this statement false? So there exists an X in R such that X is greater than 0. Okay, so we say, let's say X is equal to 10. And for all N, N times X is greater than 1. I think for this is wrong because you could there's an N equal to 0, thus ruining the statement. Otherwise, I feel like it would be true because then if you had 1, 2, whatever. There exists an X in R such that for all Y in R, should we direct negation for F? Is my negation true? Yeah, there is. Okay, whatever. G, there exists an X in R. So this statement is I want to say this statement is true. Not the negation, the first one. Yeah. H for all Y and R. for this statement, there is a y in R. This is true just while y is equal to R. And then the negation will also be true. There exists an x in the set of rationals, such that so there exists a number of rationals, such that for all n in the set of natural numbers, n times x is not an integer. Yes, this is pretty simple. So the original statement is false. So for I, you just choose, whatever the denominator is on the x. So J, there exists an x in R such that there exists a y in R such that x plus y interesting. So yeah, x plus y is less than or equal to 7, and x is greater than or equal to 7. Okay, so the truth of this statement doesn't really matter, but the original statement, if x plus y is less than or equal to 7, and is equal to x, then this implies that x is equal to 7. So basically, if y is equal to 1, x is less than or equal to 6. Then x is less than 7. The original statement is true. Let's cheat. I and J are both true. Yes. $22. Hopefully, these ones will take as long as the one bit above. There's a hope. There's an integer m such that. So okay, so there is an integer m. Oh, so yeah, okay. So again, this is the original. Such that, again, just write a comma. Or st, I guess, works fine, short form. Okay, for all Again, no largest integer. There's row number 1. There's row number y equals to x minus y to x minus y. But why do they always put it after? Like, just tell me it's at the start. So yeah, just choose y equal to 0. So true. But this would also be true. I swear this would also be true. Oh, that's not equal to 2 for all. Yeah, could we do this? So if we choose, like, choose 5 and 10. And that's negative 5. Okay, what if we choose negative 15? So 5 minus 10, negative 15. Am I tweaking? Okay, so B is true, yeah. Dude, I don't know what the fuck. Okay. Interesting. So let's see. So 8 minus 6. Okay, that's 2. This statement is true. Statement is definitely false. Let's see. So if x is greater than 3 again, so like let's say 3.1, then you already know x squared is going to be greater than 9. So if it's y is 0, anyways, the statement is true. Negation. The statement is obviously false. Oh, this statement is false. Sorry. This statement is true. D is false. Come on. The The original statement is true since x squared and quote x. Oh yes, it must be. Yeah. Okay, this is actually true. Yeah. So if it's true, right? So if x is greater than 3, then we can bring it down, which we have to, because then if it's less like 2.9 squared. Sorry, I had this backwards. If it's 2.9 squared, then and there's no like number of r that can make it bigger, right? Because if it's negative, it gets squared as positive. So there's no number to make it bigger. For any real number x. Okay, what the fuck are we reading? So x minus 1, x minus 3 is equal to 3, then... Okay. So if we expand this becomes x squared minus 4x minus plus 3, I think. Wait, sorry. So this is equal to 3. The only thing that would make this equal to 3 is x equal to 0. This has to be negative. It has to be 6. So 6 minus 1. So 5 times 3 is not. So this statement is false. Excuse me. So the negation make it true, I guess, right? So let's see. E. Bro, what? The original statement is true clearly. Again, the only thing that with x minus 1 times x minus 3 equal to 3 is x equal to 0. X equals 0. 2, like if this is 2, then this is... I swear there's no other number that makes this equal to 0. X minus 1 is equal to 3, so x equal to 4. 4 minus 1. Oh shit, I'm stupid. 3 times 1. Yes, that also works. And 6. I don't know what the fuck they're thinking there. Did I miss an absolute value somewhere? Like I'm so... way this is true is if x equals to 6. This statement, 6 minus 1, is not true. 5. This statement is stupid. Not the dumb statement. It's technically it's true, but I feel like it's dumb. Because if x equals to 6, whatever. Whatever. Guys, I so want to be done this. I can't lie. Alright. For any field F and any A and F, if A cubed is equal, then A is equal to 1. There exists a field and there exists some A and F that if A is equal to 1, then this statement is true. The first statement is false. The original is false. Let's see what they say in the solutions. The real statement is true since A minus 1. Oh, shoot. Wait. What? I don't understand that. Oh, because... Guys, that was a fucking difficult question. But I understand what's wrong with it. 1 in fields is the... but it's not going to get identity of every field, though. I'll come back to that one on my own time. Let P be the statements. right there where x 0.5 maybe, so is indeed less than 0. Oh, and the integers. No, this is true. The p is true then. Yeah, since if x is greater than 0, either x is equal to 0 or x is less than or equal to 0. If x is equal to 0, then the statement is clearly true. Alright. Write in words the definition of an unbounded function from R to R. I don't even know what an unbounded function is. We have f of x is greater than m for this one. I don't know what the fuck. No, that's a functions questions. It's greater than. See. 25, 26. AN is less or greater than for at least 1. So yeah, there exists. 27. Oh, brother. Guys, we're right at the end, too. This is fucking brutal. Review example 3.6.1. Okay. Prove that a 4-digit positive integer whose sum of digits is divisible by 3 is also divisible by 3. Interesting. Okay, let's go to review 3.6.1 and see what they're talking about. Three point 6.1. P is the assumption that n is a 3-digit positive integer whose sum is divisible by 3. Denote the digits of n by x, y, z. For instance, n is equal to, yeah, okay. To show that n itself is divisible by 3. To do so, we observe that. Okay. Okay, wait. Wait. What are they doing here? factor out of 3. Oh, shit. That actually makes sense. Okay. Let's go back down to the example. Okay. Yeah, so what x, y, z, and fuck it. Q, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X. Okay. Doesn't matter. That's not important. Anyways, so we have plus Z because W is thousands. X is the hundreds. Yada, yada, yada. Okay. Now we can regroup this. So we want to regroup it so that we have at least we can kind of group them together. So we have 999W plus W plus 99X plus X. So again, taking the same value, we just rewrote the sums as kind of more like their original parts. So now we can regroup them. 999W plus 999X plus 9Y plus, we'll leave Z. So again, just regrouping them, we know that we can also clearly factor out a 3 from this. So 333W plus 33X plus 3Y. Nothing special there. Now this, well, we said above that this was divisible by 3. So this just becomes 3K. Where K is an integer, I'm just too lazy to write it. So then we factor out a 3, we get, yeah, I'll keep that. And we're done. That's it. That's the proof. Thus, the entire thing is divisible by 3. B. Prove that n is a 3-digit part indivisible with the sum of digits of the whole number. What? Prove that n is a 3-digit positive integer that is divisible by 3. Oh, interesting. Can you write the statement into... Okay. So what n is equal to, like, whatever. We'll use the same thing. So x, y, w, x, y. Not a product. This is the sum. Just too lazy to write it as otherwise. So we know that n is divisible by 3. Where we have n is equal to... We know that this don't know where we should start. Whose sum of digits is divisible by 3? Such a good son. Okay, so because this statement is already divisible by 3, right? That means we already are guaranteed to get like 3 divides 3 plus something. If that something is anything less than a multiple of 3, like it could be, again, remainders. So 1, 2, 4, and 5, not divisible by 3. So it has to be divisible by 3. So 3 must divide this for something. So 3 does divide this as required. Can you combine this observation? So yeah, again, this is the same thing. So I'm not trying to write that, but yeah, you can just say like if n is a 3-digit integer, if n is a 3-digit integer, then n is a 3-digit. If n is a 3-digit integer, it is divisible by 3 if and only if the sum of its digits is divisible by 3. So yeah, then you just like then this way you just prove it both ways. So again, let me go down here. Forgot we had the solutions actually. This is 27. Suppose we have a 4-digit integer. Yes, yes, yes. Suppose n is a 3-digit integer, so that consider the sum a. Okay, so since n is equal to 2 I equal to 0, 10 I times a of I. Moreover, as n is divisible by 3, Where the fuck did n come from? Oh. Okay, interesting. 10i. Oh, I see what they did. I don't know why they wrote it like that, but okay. Moreover, as n is divisible by 3, then n equals to 3k for some integer. So 3k minus 3. So yeah, this also 3. So yeah, you can just rearrange it actually. That's actually a smarter way to do it than what I did. So 3k is equal to 33x plus 3y. So again, bring that over. So we get 3k minus 11? Why 11? It's already factored out. I guess, yeah, wait, why? Okay, you factor the 3. So it doesn't make sense. They factored a 3, but there's already a 3 there. Okay, anyways, it'll have to be divisible by 3. Yeah, so yeah, you just flip them. So then this would be like the forward direction, and then you can use the other one for the backwards direction. Very sloppy. I don't know if I'm doing it kind of lazy. So we're not going to do it. 28. Prove that a natural number is divisible by 9 if only it's... Okay. Prove that a natural number so it's divisible by 9. So natural number is divisible by 9 if is divisible by 9 if it's sum of digits. Divisible by 9. Okay, so n is equal to we have to use this way because we don't really know the length of the... We don't know how many digits are in the number. So... And we know this is divisible... 3 is divisible... Or 9 is divisible by n. Wise. Am I tweaking? I think that's the entire proof. Oh, they do a little bit of factoring. So I did not know how to do this. So they factor out 9k is equal to whatever plus y is there two statements here? Why? Where is this? I think this should be equal to this. Why is that there? Well, n is actually equal by n. Then n is equal to 9k for some integer k. What digits of n, if and only if n is equal to n times I, okay, times a of I. Thus 9k is equal to, yeah. So we can rewrite the sum as 9k is equal to a of whatever plus n is equal to I is equal to 0. 9 times 10 of I times a of I time plus 9. I don't know why they're already writing the sum of the digits plus the sum of n. I don't understand. Okay, I need to use the washroom. I'll be back in 1 second. Okay, I'm back. Back to understand this proof. So I understand what they did. So similar to as we did above, they had the sum of the digits plus the sum of the rest of the number, which they factored out. So that second part is just them rewriting the question. So then you have 9 times 10 over I times ai plus 1 y plus 1. because you don't have that last one. Interesting. Cool. I understand. I get it. Plus 9. Okay, so basically we literally the same thing as we had above, but it's this now it's in sigma notation. We include 9k minus 9. Okay, so this is basically the same proof, but now it's in sigma notation. So this is n. We can rewrite n as the sum of its digits, right? We rewrite it. Sorry, that was I did stutter for on purpose. Not at the beginning, but at the end I was. So my speaking is not that bad. I hope not. Anywho, so this is akin to like factoring out the 99 plus 9 plus whatever, right? So 9 times the 10 over I times the times AI plus 1. And of course we do AI plus 1 because we don't, if you notice, like if we, in any integer, the ones digit, you can't factor out the ones digit. You can't factor out the 3 from the ones digit. You just can't do it. So A at 0 is that ones digit, so we don't want to include it. So we start at 1 and then go to n. And we stop at n, right? Then we know this is divisible by 9, so we say 9k. Again, literally the same thing, and just minus this whole expression for sigma notation. We don't even have to know what it is, because property of summation, obviously, is all of you guys should know, is 9k minus 9 times n is equal to I is equal to 1, 10 of I, AI plus 1. And then we get whatever your sum is, doesn't matter. Your sum's jolly, joy. Because now it is a multiple of 9. I probably would have gotten it because I was on the right track, but we are here. 29. The function statement true or false by with the proof or counter. For any n and n, we have n minus 1 plus n is equal to n plus 1 cubed. So above, I'm pretty sure we proved this was false. So what n is equal to 9, I think I chose. Excuse me. Oh, this is squared now, so maybe I should be different. So 8 squared plus 9 cubed is equal to 10 cubed. Obviously not. So I don't know. Again, like this is just not true. So again, 29 here I think is false. Yep. 30. Holy shit. Ending this fucking, these textbook questions are like the end of a basketball game. Like the last 2 questions take forever. What x be an integer if x not 1 is, if x squared minus 1 is not divisible by 8, then x is even. So if x is odd, then okay, so we have squared minus 1 is divisible by 8, so we have that. So x is odd. So we know that x is odd, so what? X is equal to 2k plus 1, right? Then we do 8, so we do x is odd. Interesting. 1. That's not true. So my contrapositive has to be wrong. If x, what's the contrapositive of this? Then x equal to 2k plus 1 or some integer, yeah. Notice that this number is even and k plus 1 is divisible by 2. Okay, understandable. What? Wait. Okay. If k is odd, then k plus 1 is even. We arrive at the cases that x squared minus 1 is equal to AP. Okay. So, 3. Oh shit, this is true. This is true. Okay. I was tweaking. My bad. I forgot the rest of the solution. I'm gonna try to do this by myself. Okay. If x is odd, then 8 divides x squared minus 1. Okay. So, we have x is odd, so then x is equal to 2k plus 1. X squared is equal to 4k squared plus 4k plus 1 minus 1. Okay, so now these cancel out. We have x squared minus 1, or x. Now we have x squared. I'm not going to write that. We already know. So 4k squared plus 4k. Factor out of 4k, and you get k plus 1. Shoot. Okay, so now I don't remember what the solution did, and I don't want to remember, which is good. So 4k. So okay. So k and k plus 1 are consecutive integers. So if k or k plus 1 must be even. So one of them must be even. Doesn't matter which one. Either way, let's just say k is even, just for the sake of simplicity, right? Actually, this would be odd, so whatever, doesn't matter. We leave it as k plus 1. I should pick a different integer instead of k. I'm not just doubling it. I'm using the definition of it. Am times k plus 1. Bada boom, bada bing. We're done. I think it's the same thing the solution used. Yeah, if k we can write as 2j. If k is odd, then k plus 1 is even. So yeah, consecutive integers. Any two consecutive integers obviously have to be even. So like 9, 10. Pick any integer, and if that integer is not already even, the integer plus 1 will be even. What m and n be two integers? Prove that if m squared is plus m squared is divisible by 4, then m and n are both even numbers. Guys, we're right there. Holy shit. I want to stop, though. Okay, I'll prove this one, and then take a break. 30b. Let m and n be two integers. Prove that if m squared plus n squared is divisible by 4, then both m and n. So, if m and n are odd numbers, is not divisible by 4. Okay. Okay. So then we have m is equal to 2k plus 1 for some integer, and n is equal to 2m, not 2m, 2q plus 1. Sure. So 2k plus 1 plus 2q plus 1 squared. And I guess that leads me to the entire proof. Regardless of whether n is even, and regardless of which n is even or odd, we write a remainder of 1 or 2 when dividing